Okay, some announcement. We have a midterm exam on Wednesday next week. Okay, so midterm exam and no class on Monday next week. And assignment due is today, right? And I posted this reading assignment, Uart. Okay, and the timer. We will talk about this timer today. Okay, so please read this chapter. So chapter 19 and Jinx 7000 in Jinx 7000 TRM and some UART registers you need to know, right? That is, you need to know UART register for programming, right? And we will talk about this, private timer today. Okay. And today, we will finish up UART discussion and jump into timer. Okay. Let me show you one, demo. Last time we went through this hello world program, and today, echo. Okay. Second example. That example is also very simple. Take a look at this. Take a look at this UART block diagram. Okay. So you have PS, right? PS, the whole PS, processing system, and CPU inside, PS, the ARM CPU, and UART, IO device. And this whiteboard, I drew a block diagram of UART focusing on data registers, TX54 and RX54. So what you want to do today is you want to, PC, right? Teratom PC is connected to the JET board, right? So last time what you did is you are sending the ARM, right? ARM is sending hello world message to your PC through that, TX54, right? You wrote, each character H, then E, then L, something like this, right? That is what we have done last time. And today, echo. What is echo? Echo means from your PC. From your PC, you are typing some character on Teratom. Teratom, right? Teratom is running on your PC, right? You are typing something, something like hello world message. Hello, right? From here. HELLO, right? Then that should be sent to JEDBoard through this RX connection, right? Character by character. So first character that will be loaded in RX54. Okay. Then what you want to do is we want to display this character, right? You typed HELLO. You typed HELLO on Teratom, but Teratom does not display this character unless you are doing something. Okay. So what you have to do is anyway, Teratom is sending character by character to JEDBoard. So the first character will be loaded into RX54, and your program, the program running on JEDBoard, should read this character and write back to TX54. Echo, right? Echoing, you're echoing, right? So H will be sent back to PC, and Teratom will display first character H. Okay, so let me show you. Let me turn on the board and Teratom, right? Even though you type, some characters like hello, right? Nothing displayed on, Teratom, right? Because you didn't do anything, right? So you have to okay, so Teratom is sending data character by character to the JEDBoard, but your program running on JEDBoard should copy that guy copy that guy and write it to tx54 so that you can see the character. That's echo program, right? And this is the program I created, the project I created. Okay, so two programs, the echo init register definition. So Uart initialization, same macro, right? So before normal operation, you have to set operating condition, transmission speed, communication speed, and the packet format, right? So that is done with this macro. And take a look at this one. Is very simple program, right? Only dozens, few lines of the code. It's not so from here to here only, right? Super simple. Okay. So Uart data register TXRX54. If you remember that the location of 54 E000 what was that? One something. E001 E001, right? And offset 30, right? 0030. So RX54 and TX54. We are using same location, right? Memory mapped location. Okay. Let me put it side by side. I don't have to show my face to you, right? So only registers. That is important. Okay. So take a look at this. So now TXRX54 location is 30, right? Offset. And you are loading status register, right? Not loading, you are location of status register, which is this one, 2C. Okay, status register. Okay, so location, memory mapped location of status register. So what it is doing is very simple. You are reading from R1, right? R1. So you are reading from what? RX54. Reading from RX54, right? Okay, so load it to R2. Okay, this one, status register. Let me show you status register detail. Where is that? This one. Okay, channel status register. Okay, status register detail. So you are reading status register information in R2. So this information. Okay, this information in R2. Then you are doing what? AND operation with this one. One bit shifted left. One bit shifted left. So what you want to do is you want to check out this RX empty bit. Okay, empty. So that means is it empty or FIFO? RX FIFO is empty, meaning nothing has been received. Empty means nothing has been received. RX FIFO, right? This RX FIFO. Nothing has been received. If it is 1, RX FIFO is empty, right? RX FIFO 1, that means RX FIFO is empty. So it is RO, read only bit, right? Read only. With your program, you are supposed to read only, right? Write operation is not permitted. Write operation, store operation is not permitted, right? So RX FIFO, empty, right? So you are extracting only this bit, RX empty bit, and compare that next instruction. Compare, right? Compare that against 10. Okay, equal. Okay, R2 is equal to this number. That means what? FIFO is empty. Okay, FIFO is empty. Nothing. No character has been received yet, right? So you are jumping, you are branching back to this label. So you keep checking this one. You are keeping checking this empty bit. empty or not. Not empty, okay, not empty, then you fall through. Not empty means what? You have received some character, right? You have received some, character here, character. Okay. So next instruction. Okay. Let's fall through. Then R0, right? R0 is what? R0. Data register, right? You are reading from what? Reading from data register, RX54, and stored into R3. Okay. R3, R3. So the data you read will be written to TX54. Okay. So here, read from RX54. Okay. Write to TX54. Okay. This. Okay. So you are reading data from RX54, and the data will be written to TX54, right? So R0, R0, right? We are using same memory mapped location, right? We are using same memory mapped location both for TX54, RX54, right? In hardware, they can be differentiated by looking at control signal, right? Read operation, write operation, store operation, right? STR. If you execute STR, then store operation, memory write operation, okay? Register write operation. So then you are accessing TX54, right? LDR instruction, read instruction, right? Read, memory read, or register read. Then you are accessing RX54, right? This guy. So from Uart point of view, hardware point of view, by looking at this control signal, control. What control? Read operation or write operation? It can distinguish which register, which FIFO you are trying to access, right? Okay, then what is this? This one is you are writing. So we have done this operation, right? So far, right? So read from RX54 and write to. So that will be displayed, right? That will be displayed at this point. Okay. And next instruction, what is this? Compare if the data R3 data you have received is equal to 13. What is 13? 13 is carriage return in ASCII code. That means you typed here. You typed here HELLO, then return, right? Return. Okay. You type return. Then if the data I have received is equal to return 13. Okay. Then I'm going to send out additional data. Okay. So R3. So R3 is already echoed back. Even return, right? Carriage return. 13, right? If the data is 13, and that is written to 13 here, right? So that is transmitted. Okay. So in addition to this data, and I'm going to send one more data, 10. Okay. So internally 13 and 10. When I receive 13, okay. 10 is what? 10 is line feed. So it turns out that if you type enter, then I did many experimentation. If you type enter from PC, it is only sending 13. That is why I wrote that program. Okay. Again, if you type enter from your keyboard, okay, from PC, then I figured that RX54 has only 13, not 10. No 10, only 13. So that is why I'm sending the data here, echoing back. Then one more, right? Carriage return and line feed. Carriage return and next line. Okay. And a branch, loop. You keep doing this. Right? You keep doing this operation. Simple, right? Very simple, right? So let me show you a demo. So demo, compile it first. Compile, build. Okay, then download it to the jet. What is that? Okay, I did some experimentation in the previous class. So exiting the previous debugging session. Okay. What is that? Okay, let me do it again. Something went wrong. Okay, then initialization, press F5, then reading from data register. Oh, sorry. Memory mapped register information. Memory mapped. Okay, sorry. Memory mapped location of that data register, right? And memory mapped location of status register. And you are keep checking. So let me press F8, right? So that the program keep doing this operation. If you press F5, right, it is doing this. Nothing has been received. I haven't typed anything. Again, it is checking, right? Status register. Okay, this bit is empty bit. Still empty, right? I haven't typed anything from terminal, right? From this terminal, I haven't write anything, right? So nothing. So we keep checking this, right? So let me press F8 and switch it to this Teratom and type something. Okay. So if you type H, for example, here, nothing happens, right? But I think it'll exit. 5, exit, right? So press F5, display H. So let me press F-E. Which one? E. Okay. Then, okay. Now exit because I typed E, right? RX5OS contains one character. So now read and write E. Okay. So let me press F8. Then keep is running, right? Running state. You can type hello world. Right? It is working fine. Okay. Like this. Echoing, right? Okay, any question about this? Very simple, right? Very simple actually program, but you need to understand what's going on inside the UART, right? And UART, again, UART is very widely used IO component, IO device. In base system design, UART is always there, always, right? UART is usually used for debugging purpose. Something like you are receiving some message from the computer, right? When you boot Linux, for example, Linux is sending out, the booting message through UART connection. So you have UART, terminal UART connection established, then you will see a lot of message, coming out from your PC. Now even so, if you take a bus on your way to school, then check out that the display the panel. So inside the bus, there is a display panel. There is a UART connection. I saw that UART connection, really, 9-pin UART connection. Still, very, very widely used. Any question before switching to timer? Okay, then let's. There's UART, then timer. Timer also, timer is, super simple I/O device, but I don't know how to emphasize the importance. Very important. Every, computer system has timer, right? So where do you want to use timer, right? To display time, right? This time. Have you heard about this terminology called RTC? This term, RTC, real-time clock. Real-time clock, that is 32768 kilohertz, RTC. Okay, so RTC module, IO module, is taking that clock as an input and do something and output. RTC, IO device or IO module. So this number is familiar to you? 32.768. Okay, that is what 32.768 hertz, which is 2 to the power of 15. Okay? So RTC. So if you have a clock running like this, which is so this one, and if you divide this clock, okay, by 2 using clock divider, okay? Clock divider, and do one more divide, one more division, right? Like this, okay, and one more time, right? Like this. You keep doing this 15 times, you get what? 1 hertz. You get, that is 32.678 kilohertz, right? And 16,384, right? Kilohertz, 8192 hertz, 4096 hertz, and keep doing this, right? 20, 48, 10, 24, 5, 12, and so on, right? Then eventually 1 hertz. So every second, every 1 second, right? Every 1 second, you have 1 pulse. So that is 1 second, right? Every rising edge of the clock, you increment time, right? Time, second. So that is window is displaying this time, right? This one, this time, right? 3, 4, 5, 6, RTC, right? Real-time clock. Okay, so one example. And timer is also used. Timer, is used to generate PWM, pulse with modulation, PWM signal. Remember, DC motor example. Let me show you that. Where's that? Sensors. Not this one, DC motor. This one, ADC. Right, this one, right? That is PWM, pulse width modulation, right? So the on duration is 1 millisecond. Then this DC motor is rotating, this amount, right? And on duration, 1.5 millisecond, 90-degree rotation, and so on and so on. So that is PWM, pulse, right? This is pulse. PWM, pulse with pulse width, right? Pulse width. That pulse width. Right? Modulation. Right? So how would you generate that pulse? That periodic pulse. Okay. Timer can be used to generate this PWM, right? You can measure the time. Okay, you can measure this time. Okay. So timer can let you know, okay, this is the time to this is the time to let this signal force this signal to force this signal to deassert, right? And this is the time. This is the time. This is the time. This one is time, right? So this is the time to assert that output. Okay. Let me use different color. This one. Okay, let me use different color. So one timer, probably one timer. Okay. Periodically let you know, okay, this is the time, periodic, right? And another timer can let you know, okay, this is the time. Okay. So this time probably you can deassert this signal to 0, and this time assert this signal to 1, and this time. So timer can let you know, okay, what this exact time. Okay. And operating system is using timer, right? OS, right? For scheduling, task scheduling. So every 1 millisecond, every 10 millisecond, task switching is done. How does the CPU know, right? Think about that, here, time. So every 1 millisecond, right? 1 millisecond, 1 millisecond. So this is the time to schedule new task. You have to, I'm CPU, right? You have to let CPU know, okay, through interrupt. Don't worry too much about interrupt. We'll talk about that after midterm exam. Anyway, timer is generating periodic interrupt like this. Okay, 1 millisecond elapsed. This is the time to schedule new task. Okay, so OS. Okay, OS is running Hello World so far. Then switching to MP3 player. And next time, Chrome. I want to surf the web, right? And next time, what? I need to cook up documentation, HWP, something like this, right? So OS is intensively used timer for task scheduling, right? So timer is essential, very essential component. Right? Talk about this. Okay, timer, this is the alarm clock, right? So timer is like alarm clock. You use your finger to set up, the time, right? So before you go to bed, in the evening, you set up alarm clock, and alarm goes off in the morning, right? You set the time, right? And the clock, this watch, is comparing current time against the alarm setting, right? Then if these two are equal, alarm goes off, interrupt happens, right? Same mechanism, right? So inside Zinc 7000, you have a lot of timers actually. So you have two CPUs, two ARM CPUs, right? CPU 0, CPU 1. In our class, we are using one of them, right? So you have here, if you debug, right, this one. If you run, and two CPUs appear here, right? CPU 0 and CPU 1 appear on this pane, right? And we are using one of them, right? Two CPUs, right? So two CPUs, okay? And each one has two timers, private timers. First one is called watchdog timer. Second, private timer. We will talk about this private timer, okay? And system-wide watchdog timer. So one system-wide watchdog timer, and there is a timer called global timer and triple timer counter. They are very similar. Functions are very similar, right? You want to measure the time. That is the one. Okay. So we are going to focus on this private timer, okay, in this class. Okay, private timer. Okay, Kono, can you please?
Private timer, 32-bit decrementing counter, generate an interrupt when the counter reaches 0, single shot or auto reload configurable initial value, use peripheral clock.
Okay, thanks. We have a 30-bit counter. The function is very similar. Okay, function is very simple, super simple function. So counter, right? How would you design counter in hardware? If you recall your memory, I know you don't remember anything, but let me draw timer, right? Actual timer, right? The clock, right? Sorry, D and Q, D flip flop, okay? D flip flop, and then how would you design timer? Okay, flip flop, then for example, 32-bit. That is timer output. Okay, then decrementing counter. How would you design? So clock is something like what? Let's say 50 megahertz. Okay, and then you have what? You have adder, right? That is connected to here, right? So that output is connected to adder. Okay, second input, decrementing. So every clock cycle, you want to decrement this number, right? Let's say the first number is 100. Okay, here. Okay, so 100, rising edge. Okay, then you want to decrement 99, 98, and so on, like this, right? So you have to do what? Decrementation, subtraction, right? So you have to provide what? -1. -1 is what? In computer, 8 Fs. That is -1. So this adder is doing addition operation of this input and the number, then decrementing, right? So that is timer, super simple. So you have to, let me show you the function like this. Okay, here, that is timer. Timer block. You have private timer, IO device, and using this clock out, you want to do decrementation. Okay, so 100, 99, 98, and so on. Super simple operation, right? And counter becomes 0, then something happens. Depending on your setting, configuration register setting. Usually, interrupt is generated. Interrupt. Okay. If you don't want to use interrupt, then keep checking status register. That is called polling method, right? Two different approach, polling or interrupt. Okay, so after midterm exam, we'll talk. Okay, today we'll use polling. Simple. You keep reading the status register to check out this timer. Timer value becomes 0 or not, right? You keep checking, polling. That is waste of computing power. Why do you want to keep checking on status register, doing nothing? Keep checking, right? You have a lot of useful work to do, right? Why do you want to keep checking the register? That is a waste. Anyway, we are going to use that mechanism. So using clock out, so that is clock in in our private time. I think, what is the clock? Do we have some information? Exact input clock. I'm looking for input clock speed. Okay, here. That is our the input clock speed, 333 megahertz. Okay, that is the private timer input. Okay, but for simplicity, let's use this one. Okay, 333. This one clock input, 333 megahertz. For simplicity, let's assume 100 megahertz. Okay, and depending on the register you set, you can use clock divider inside private time. Okay, you can set prescaler. Where is prescaler? Okay, so let me show you. Only 4 registers. Okay, only 4 registers you have. What you have to do is you set control register. That is configuration register. Remember, 3 kinds of registers in IO device, in any IO device, right? The first one, configuration register. Before normal operation, set configuration. Second, data register, right? And status register. Control register is configuration register. Okay, and you have counter register and load register. Okay? Very simple. First, control register. Let's read this. Okay, read first, then explain. Okay, this one, Mingyu, can you please?
Clocking. All private timers and watchdog timers are always clocked at half of the CPU frequency.
Okay, so private timers are working based on half of the CPU frequency. In our CPU is running at 666 megahertz. So divide the number by 2, right? Half, right? Half. So that is why we have this number, 333 megahertz. Okay, next one. This one, Jisung, can you please?
The timer load register contains the value copied to the timer counter register when it decrements down to 0 with auto reload mode enabled. Writing to the timer load register means that you also write to the timer counter register. The timer counter register is a decrementing counter. The timer counter register decrements if the timer is enabled using the timer enable bit in the timer control register. If a Cortex-A9 processor timer is in debug state, the counter only decrements when the Cortex-A9 processor returns to non-debug state. When the timer counter register reaches 0 and auto reload mode is enabled, it reloads the value in the timer load register and then decrements from that value. If auto reload mode is not enabled, the timer counter register decrements down to 0 and stops.
Okay, thanks. Load register. Okay, load register and counter register. Okay, we have this load register and counter register. Okay? It's very simple. Let me show you this one. This is the function. You have a load register. You can program some value. Okay, some value 100, for example, and that will be loaded. So initial value, the first value you want to count from. You want to count from 100. Okay, that is the data, or anything, any data. And then hardware timer will copy that value into counter register. Then start decrementing. 100, 99, 98, and so on. Okay, so load register, right? And then eventually the counter value, the value in counter register becomes 0. Then depending on your setting in control register, interrupt can be generated. Okay, and then this value, the data in load register is copied to to counter register. Then decrementation again, right? So depending on also your setting, the private counter is providing 2 different operating mode: single shot mode and auto reload mode. Very simple. Single shot, only one counting, 100 or 20. That's it. No counting, no more counting. Auto reload, periodic mode, right? This is auto reload, example of auto reload, right? This one. So one counting and reload, right? They reload this data to counter register, then decrementing again. If counter becomes 0, then loading again. Periodic, right? Periodic mode, auto reload mode. Okay, that is the one. Then look at this. Auto reload mode is not enabled. Stops, right? Stops. Okay, so single shot mode. And this one is information about control register. The last register we have to know, right? This one, control register. Configuration register, in other words. Before normal operation, set up configuration. What is that? What kind of configuration you can set? First one, prescaler. Jinu, can you read this one? Prescaler.
The prescaler modifies the clock period for the decrementing event for the counter register. See calculating timer intervals on page 4-2 for the equation.
Okay, prescaler, right? So prescaler, right? This one, clock divider, essentially. That is the equation. This is the equation. You take input 333 clock input megahertz. Then you want to generate the internal clock. Okay, using that formula, that is clock divider, and you want to use that clock, right, for decrementing operation. This decrementing operation. Okay, using that clock out, then decrementation. In this example, right, if you set prescaler to 3, here 3, then you are dividing clock input by 4. So you get 25 megahertz. So that is 25 megahertz clock. Okay, that is used for decrementation. Very simple, right? And look at this. Second bit, IRQ enable, interrupt enable. Right? You enable this bit, then interrupt will be generated. And first bit, auto reload mode, right? Single shot mode or periodic. Okay, 0 single shot, 1 periodic. Simple. Timer enable, right? You are enabling timer. You have to enable, right? So that is one. That's it. It is that simple. And the one last thing. Okay, status register. Let's read this. This one, status register. Okay, we know load register. The value will be copied to the counter register, then decrementation. Right? And status register. Sorry, control register and status. Check out status register. This one is a little bit confusing. Okay, Guyon, can you please? Only this part?
The event flag is a sticky bit. This is automatically set when the counter register reaches 0. If the timer interrupt is enabled, interrupt ID 29 is set as pending in the interrupt distributor after the event flag is set. The event flag is cleared when return to 1.
Okay, so after graduation, if you want to do firmware programming, especially device driver programming, you have to read this data sheet or technical reference manual a lot, right? So you have to figure out which register you have to set or read, okay, if you want to do device driver programming, right? And then probably you would encounter this statement. What is that? Event flag, this one, sticky bit, automatically set to 1, right? When counter register becomes 0. Counter becomes 0, okay, this one. Counter becomes 0, then hold on. Okay, counter becomes 0, then status register, right? Hardware will set status bit to 1. You have status register and the last bit. Last bit is the one you have to access, 0th bit, right? 31. That will be set to 1 if the counter becomes 0, then that bit will be set to 1 by hardware, right? And then think about your periodic mode. You periodically loading that the value in load register to counter register, then decrementation. Okay, then one counting down 102 0. Second counting 102 0. And third count periodic, right? Then at this time it is trying to set this one, right? At this time trying to set this one, So in the meantime, right? After setting up this bit to 1, then using software, you have to clear that bit to 0, right? So that next countdown, hardware set this one to 1 again, right? So hardware software collaboration, right? Hardware will set this bit to 1. So software, right? You have to clear that bit to 0, right? Clear that bit to 0, software, right? So hardware set, software you clear, and hardware set, software you clear, right? So then how to clear? According to the specification, event flag, that flag will be cleared if you write 1. Okay, so you have to do this. You have to store R0, for example, and then this location, this one's supposed to be 1. You are writing 1, 2, this one, then it will be 0. A little bit confusing, probably. Okay, you are writing 1, then how come this one becomes, you are writing 1, how come this one becomes 0, right? But hardware, right? Hardware was designed that way. How would you design? Very simple, right? Think about hardware implementation, Verilog implementation. Very simple, right? If data, right? Verilog, right? Data is equal to 1, and and address. I'm talking. This is not software. This is hardware implementation. Data address is equal to, what is the location? Memory mapped location. Okay, base address F8, F0, right? F8, F0, 0600, and offset is C, 0C0C. That is a status register. And write operation. Write operation. Then you are status register, status reg 0. Simple. Right? Hardware implementation. You are writing 1, but status register is 0. Right? Verilog, right? Talking about this Verilog. HDL, hardware description language. Right? So sometimes confusing statement, but it is not that hard to understand, right? So implementation, hardware design is done this way. Event flag is cleared. Event flag will be 0. If you write 1, right? So you don't have any choice, right? You don't have choice. You have to follow the rule. That is the rule, right? Hardware designer provided defined that rule. You have to follow that rule. Right? Okay, so let me show you demo. Okay, so our base address, private timer base address is this one. So from this base offset, right, 048C, okay, to access those registers. Put this one side by side. I have to show the board for this. Okay. Close the project. Design. Okay, close this one. Then private timer. This one is this one. Private timer, right? This example code. This private timer example code. Okay. I created this project. Very simple, very simple code also. So here, look at this. This header file, right? Header file. Okay, this one. So here is private timer, right? Timer base location and load register, offset 0, counter register, offset 4, control 8, status C. Okay. So now, don't worry about this, first 5 instructions. This one, MRS, MSR, we will talk after midterm exam. So private timer setting. Okay. Load register, memory mapped load register. Okay. Talking about this. This load register. This load register, then count, right? So load register, memory mapped location, and interval I set to 4. How many zeros? 5 zeros. That means roughly 4 million. I want to count 4 million clocks. 4 million, right? So here. So starting from 400,000. So this number, 400,000. Then counting down. So roughly, if you interpret this one, because 5 zeros, right? Five zeros, right? 0x for 5 zeros, which is, so that is 20 bits. 20 bits. Okay. So that means 2 to the power of 20. So that is 24, 10,024. Okay. So roughly 1 million, right? Roughly. Right? Not exactly 1 million, but just 1 million, right? 10 to the roughly power of 6. So you want to count 4 million clocks. Okay, for roughly. Okay. 4 million clocks. And that is the, okay, so load register 4 million, then control register. I said prescaler. Here. Okay, prescaler to 10. This one, this bit. 8 to 5. Okay, so how to set? 8 bit shift left. 8. Start from 8. There is 8 bit shift. That is why. Okay. So prescaler 10. That means what? I want to create what clock? So that clock from this slide. That means what? So input clock. Let me use. Input clock 333 megahertz. Okay. Divide the number by what? Prescaler is 10. Then 11 plus 1. Okay. Divide by 11. So roughly 30 megahertz. Okay. That is counting clock. 30 megahertz. Okay. That is a clock. 30 megahertz. Then how many countdowns in 1 second? What do you think? We have this number, 4 million. We have roughly 4 million. Okay, it is counting down 4 million, then 30 million megahertz, 30 megahertz. So, we are going to estimate, we want to estimate rough number. So every second, what is the number? Every second, you have 30 million clocks. That is the meaning of this, frequency. Okay, then you want to count this 4 million. Then in 1 second, probably roughly 30 divided by 30 divided by 4, roughly 8.25, right? Roughly 8. 5 count downs. So roughly 8 countdowns in 1 second, right? 8 countdowns, periodic, So there is a one. So here, so you set up control register, load register. That's it. It is that simple, right? Then reading from counter register, just for test. Okay, R0, R0, R1, R1, R2, R3, R4, and so on. So just want to read, just want to check if the counter is really decrementing or not. Just want to check, right? Then here, status register, sticky bit, remember? Okay, R1, sticky bit. So what is this? Turn on LED just for testing. Okay, LED. Then what is this? Forever, right? Forever loop. Then read counter for testing. It doesn't have any meaning, just read counter. Then second is important. Read from status register to check out polling, right? Polling to check out this value is 0. right? This value is 0. Okay. L6 is 1. Then count down, whole count down, right? The 0, right? You reach it 0, right? So you are doing what? You are doing that operation. EQ, remember EQ? EQ, EQ. Compare instruction is setting flags, NGCV, in CPSR register. So next instruction, checking flags to determine, execution or not execution, right? So, counter is 1. Sorry. Status register is equal to 1. Okay, meaning this point, right? Meaning this point. Then you are doing what? R11. What is R11? R11. R10, sorry, R10. R10. LED. LED. Toggle. You are keep toggling, right? LED because you are doing XOR operation. Time. Okay, we have time. Okay, we have time. XOR operation is very useful, right? That is one usage. You are inverting things. XOR operation. Exclusive operation R11, right? Then that is XORed with FF. Okay. So the value R11 is 0F at the beginning, right? 0X, 0F. Then you are doing XOR operation with F. Then what do you get? You get 0X, F0. Okay, 0, F, 0. XOR operation, right? Remember, you have exclusive OR gate. A, B, Y. Think about truth table. 0, 0, 1, 1, 0, 1, 0, 1. Right? XOR 0, 1, 1, 0. So, FF, all ones, right? 8 ones. So that condition. Second input is 1. Then you are toggling 0 to 1, 1 to 0. 0 to 1, 1 to 0. Right? So I'm trying to. So every countdown, I want to toggle LED. Okay, starting from 0F. 0F means what? 4 LEDs will turn on. Right? We have 8 LEDs here. So first 4 will be turned off. Right? 0F. And last 4. Okay. Upper 4 and lower 4. Lower 4 will be turned on. Okay. And first countdown. Okay, after first countdown, then you are toggling, right? R11 will be F0, meaning first 4 will be turned on and turned off, right? And next iteration, forever, right? Okay, periodic mode, right? Periodic counting, right? So, okay, let me show you the demo. Compile it first. Build. Is it done? Okay, so then debug timer counter. Okay, registers. Close it. Let me execute until this line 40, right? Line 40. Fast. Okay, here. Okay, we set up everything. Then read from counter register. We set load value to 4 5 zeros. Okay, so counting from this number. Okay, so check out this R0, R1. Okay, R1 first. R1 3 1 1 decremented. Okay, 3 5 Fs. Then R2 E. Okay, one more decremented. T C P A 9 9. Well, why 9 9? No decrementation between 7 and 8. Between this one. So why do you think so? Because counter, right? Timer is slower compared to CPU, right? CPU is running at 666 hertz, whereas counter clock, we created the counter pretty slow, right? How slow? What is 30 megahertz, right? We created 30 megahertz clock, counting clock. Okay, compare that against CPU, 666 megahertz, and program is running with that clock frequency, right? So now status register. Okay. Show you the board. 5 status register R1, then LED, right? F. So at this point, if I press F5, then 4 LEDs will turn on, right? 4 LEDs. 0F. Okay. Then this forever loop, forever. Counter value R5, still big number, 3FF. You have a long way to go, right? To become 0, right? And then status R1, okay, R1 status register. R6 will be 0, right? Not yet this one, this bit. This is not yet 1, right? You have a long way to go, right? So then next instruction, compare R6 against 1. R6, R6, it is 0, right? So not equal. So 0 flag is 0, not equal, right? So that instruction will be, those instructions will be silently changed to no operation inside the CPU. Okay? CPU is not executing these 4, right? So no, nothing happens forever. So let me press F8 because I don't want to press this many times, right? So let me press F8. Then what do you expect? Then in 1 second, roughly 8 countdown. So that will toggle very fast, right? 8 toggles in 1 second, I think. Let me press F8. Right. Roughly 8. I don't know, roughly. Right. So again, polling method, because we are checking this one. This is a polling, right? Keeps reading status register to check, check that countdown. Okay. And one more useful thing is, scroll, check out this MP core. You can read. Here. You can read here, private timer registers, load register. Load register reset, 400,000, right? And control register reset. Here. Prescaler 10, which is A, right? A. And 7 is 111, right? In binary. This one. We set 111, right? IRQ enable auto reload enable, timer enable, right? So you can check registers. Okay, CPU is providing. So each CPU, right, has private timer and global timer. Okay, so something like this. So you stop it, then you can check. You can check counter register. Okay, you stop it. So there is current count 3, 4, 8 something. Run it again. Stop it. 2, E, 5 something. Count. Okay. And do it again. Stop it. Okay. D730 counter register. Okay, that is everything I have for today. Any question? Everything is clear, or you don't have any clue? Either of both. Either right? Either of these two, right? You don't know what's going on, or you perfectly understand everything. Okay. Okay, I'll see you next Wednesday, right? Next Wednesday in class. Okay, classroom I think 302. 애기는 생활관. Okay. Exam, right? Midterm exam. Okay, I'll see you next time. Bye. Okay. Thanks.